Okay, so if we're gonna look at something for the molecular orbital picture, let's just make it a little harder on ourselves actually than I did in class. Okay, so we have a molecule here, and what we need to do, we're going to do an elimination, so we're going to do an E2 elimination, one step. What we need to do is get this lined up into an anti-periplanar conformation. So the easiest way to do this, I think, is to get your leaving group, in this case bromine, lined up with H. And I like to put them in the plane. So that means your leaving group and whatever H you're taking away are not wedged and hatched. So in this case, we're going to have to rotate about this bond. Right? So if I rotate right, there, I keep this stereocenter, this center the same. So if I label this carbon 1 and carbon 2, I don't move carbon 2 at all, but I rotate carbon 1 to get the bromine where the methyl is. So the methyl goes back, the H comes forward, and the bromine goes back. So these kind of rotate around there. So it would look like, here's the bromine, now the H is forward, and the methyl is going back. And this is all the same. That's still an H. But now you have your anti-periplanar relationship, right? So you might have to rotate some bonds to see this. Now, the question at hand then, of course, is how do I know, how does this work? Well, sigma star, the reason why it has to be anti-periplanar is because sigma star for the carbon-bromine bond, right, is 180 degrees away from this carbon-bromine bond, which lines it up perfectly with this CH bond, right?
180 degrees away from the hydrogen?
No, it's the CH bond is even with the sigma star. Okay. It's right face to face, right? Sigma star is 180 degrees away from the bromine, just like the H is 180 degrees away from the bromine. Okay. Right? So what happens, our base comes, takes the hydrogen. As it does that, the 2 electrons here go into sigma star, which forms that new pi bond. And as those electrons go into sigma star, the carbon-bromine bond, of course, breaks. So there's 3 arrows. Now, we know we're going to form a pi bond. And there's a reason why back here I wanted to have the bromine not be wedged or hashed and the H not be wedged or hashed, because it matters for alkenes, right? Because can alkenes be cis or trans? Yeah. Yes. So you got to be careful here. So if you look at, once I got this lined up, right, in the anti-periplanar conformation, this H and this H were both coming out at me. That means they're both going to be on the same side of the alkene, right? The methyl and the other methyl are both wedged or hatched and going back. So it means they're both going to be on the same side of the alkene. So I just think it's easier to get these things lined up, right, not be wedged or hashed, because when you draw your alkene, then it's easier to see what's cis to each other in the alkene. That's why I like to do it. You don't have to do it this way. This is just the way I like to do it. So question came up about how could I do a non-Zaitsev product? So there's beta hydrogens over here in this methyl, as well as these 2 beta hydrogens. The difference between these is this carbon is a secondary carbon, right? It's a carbon bond to 2 other carbons. This is a primary carbon, a carbon bond to 1 other carbon, right? So normally with a small nucleophile, we're going to want to form Zaitsev's product, the most substituted alkene. But if I used a much bigger bulky base, say like something like tert butoxide, I might start to get some of the non-Zaitsev product. But normally I need a big bulky base and a tertiary alkyl halide. This is only a secondary. So it's possible to start pushing to form different products, but you really usually have to like really bulk the sterics up quite a bit to get it to work. All right, so let's look at ways to instead of getting the Zaitsev product, the most substituted alkene, how can we take advantage of reaction conditions and get the non-Zaitsev product? So one of the ways to do that is we have to use sterics to our advantage. So you have to have a tertiary alkyl halide first. You must have a tertiary alkyl halide. And you must have a really bulky base. Right? So the way this works, so because this is so sterically bulky, and so is this, right? If we count the types of beta hydrogens, right? Let's look at our beta hydrogens. That's always the first thing we want to look at. So we have a beta carbon here, we have a beta carbon here, we have a beta carbon here. Draw our H's in. Right, so how many types of beta hydrogens do we have here? Two types. Right, so we can form how many different types of possible alkenes? Two. Not thinking about cis and trans, but two types of beta H's. All right. Okay. The question is, which one's more likely to happen? So let's look at these alkenes. Let's look at these carbons. These two types of beta carbons. So what's different? So these beta carbons, if I numbered them 1 and 2, so 1 and 2 are both primary carbons. So they're automatically more sterically accessible, right? They're easier to get to. There's less carbons around them. Whereas this carbon, carbon 3, right, is a secondary carbon. So it's going to be a little more sterically bulky, right? It's going to be harder for the base to get to, right? So because it's harder to get to, it's more likely to attack these H's just because of sterics.
But if you didn't have a bulky base there, would it attack?
If I didn't have a bulky base, no. Then it would attack carbon 3 H's, the beta hydrogens on carbon 3. And form the more substitute. Yeah, so if you don't have tertiary alkyl halide and a tertiary base, you can't get this to work. You need both things. You absolutely need both things. So in this case, you'll get this product plus, right, Br minus OH. Right.
So you need tertiary alkyl halide and what for this?
A bulky tertiary type base. Okay. Yep, you need both of them to be tertiary.
Bulky tertiary base?
Yes.
Okay.
So non-Zaitsev. But you need both the tertiary alkyl halide and the big tertiary bulky base.
Did you get also the pi bond in the card?
Right, but that's the point, right? So forming a pi bond here is the same as forming a pi bond here.
Same thing?
Right? If I rotate around that bond, it's the same thing. Right? Because both those beta hydrogens are the same. So they both form the same product, right? That's why I want to get us thinking about the number of types of beta hydrogens is equal to the number of types of alkenes we can form. So let's talk about solvents. Solvents for SN1 versus SN2. So the best way to think about this, I think, is in SN2 reactions, you have good nucleophiles, good nukes. And that usually means a negative charge. And that usually means you don't want a protic solvent, right? You don't want, if you have, here's the thing, right? If you have CH3O minus, and that's a good nucleophile, right? But if you put that in water, it's going to react with water, right? It's going to act like a base and react with water, right? And that's not what you want to have happen, right? Because now all of a sudden, instead of having CH3O minus as your nucleophile, now guess what your nucleophile is? OH minus, right? So in SN2 reactions, you don't want to be using polar protic solvents. You want to use aprotic solvents, right? No hydrogen bonding with themselves, so right? DMSO, right? There's no OH, NH, SH, pH bonds, so it doesn't do hydrogen bonding with itself. And essentially, SN1 is just exactly the opposite. SN1 doesn't have good nucleophiles, so it wants polar aprotic solvents, solvents that are really, really polar. So protic solvents, right? Think about hydrogen bonding, right? They can make the solvent really, really polar, and that's important for SN1. Why does SN1 want polar protic solvents, you think? That are really polar. Yeah. Are carbocations pretty polar? Yeah, right? So if you're gonna have a really polar intermediate like a carbocation, the more polar the solvent, the more able it is to help stabilize that, the better, right? So if you have something, if you have a carbocation sitting there, you want a really polar solvent to help stabilize that intermediate. It's already bad enough, right? Carbocations are bad. They're hard to make, right? They're high in energy. So if you have a solvent that can help stabilize it, that makes it that much better. And polar protic solvents, right, because of the hydrogen bonding they can do, can help really stabilize carbocations. That's why they're more likely to take place.